Hello, everyone. Welcome on this lovely rainy day post spring break here. Glad folks got the notice they could show up here for our fourth Pathways series of the semester. So we're kind of busting into gear here. We've got, I think, another 4 planned for the rest of the semester, this and then 3 more. So today we've heard a bunch of different things from a bunch of different groups. I'm really excited to have Mark here today to talk really on the robotic application side and really kind of to think about how we use robots for all kinds of different areas. We think about robots underwater, we think about drones, we think about inspection. Well, Mark and Walter P. Moore, who a company that I'm sure everyone, when they saw it the first time, said, "Who's this group here?" Is actually doing a lot of really cool stuff with them. We've been in touch with them for about 8 years now, and they've been working with us on a bunch of different projects and ideas. And so today we're going to hear a little bit about the work that they're doing and also talk about this interesting partnership that we're doing with potential fellowship opportunities and summer internships that can kind of go together hand in hand with her. So with that, I'm going to pass it over to Mark.
That's perfect. Yep. Damon. Thank you for having me. I want to talk about autonomous reality capture for the built world. Again, I'm Mark Williams. I'm with Walter P. Moore. Just some real quick background on Walter P. Moore, and we'll get going. We're about 1,200 person engineering consulting firm. We handle multiple disciplines. So by that I mean we do structural engineering, we do traditional civil engineering, so that all your site work, drainage, and all those things that go with it. And then the group that I'm in, we call diagnostics. And diagnostics means we look after the built world. So there's things that already exist that perhaps weren't built quite right, or you want to change their use, or they're starting to deteriorate and fall apart. So we come in to evaluate them further. I want to start by saying the importance of adopting new technologies. I know it's preaching to the choir here, but from an industry standpoint, innovative technologies enhance our quality of work and contribute to our mission to ensure public safety. As civil and structural engineers, we're charged with protecting public safety at the end of the day. From a company standpoint, from Walter P. Moore standpoint, self-reliance in this technology gives us more market freedom and enables autonomous reality capture opportunities. So lets us be very free to do what we want to do without having to rely on others. So I said we play in the built world. So if you could imagine the built world for a minute, or you let Gemini imagine what it thinks the built world is. I think this is a fun exercise to see what it thinks it is. But you have bridges, cable-stayed bridges. You have dams. You have ports. You have roadways, cities, and so forth. All of this is built and needs to be further investigated over time. Interesting that Gemini thinks train tracks just go off a cliff into the water.
Thelma and Louise style.
Thelma and Louise style, that's right. So my task and the task of people that I work with is we have to go out and investigate the built world, whether it be a bridge, a building, a dam, so forth. And we really need high quality data capture with that, and preferably want it to be autonomous. And the reasons for that, there are many, but as engineers, historically, traditionally, we used to go to the site and we used to spend a lot of time on site, note-taking and documentation. And we would get hot and sweaty and cranky and make mistakes and put things in the wrong place and all that. We really weren't using all of our brain power that we went to school for and really developed into. We should be making judgments about the condition of things, not being fixated on taking notes and documentation. So we're really pushing autonomous data capture, and I'll get into this more as we go. From an autonomous standpoint, we would very much like to be able to capture the air, land, and the sea, whole parts of the built world. So let's ask Gemini what it thinks we do for a living. Not bad. I could critique a few things, but let's take drones, for example. So drones are up in the air. You can use them to do thermal scanning, and I'll get into that in a little bit. You can do them to do bridge inspections. A lot of things you can do with drones. You have LiDAR on them. You can take imagery. If you are talking about terrestrial data capture on land, you could use rovers, for example. And so it's pretty smart. It's figured out that you're going to drive a rover around, you're going to scan a structure and perhaps look at the foundation, as long as that foundation's above the ground. And then lastly, we have the underwater data capture. So it shows us a submarine, and it says we can use sonar, we can do pylon inspections, dam base inspections. Gemini's actually pretty smart here. I guess it's figured out our profession without really knowing who we are. But that's generally what we're going after here, is we want to be able to capture data from the air, capture it on land, and capture it underwater. We've adopted a digital workflow for this, and I'm going to walk you through this, but this is how we envision it at Walter P. Moore. On the left side, you have data acquisition. Data is coming from a lot of different sources, preferably autonomous sources, and we'll get to that. So just to run down the list here, aerial surveys, so that would be drones capturing data. Laser-based, LiDAR, so that could be on a drone or that could be terrestrial-based. 360 cameras, great for doing interior scans. Drones are great on the outside primarily. Non-destructive evaluation, so using different tools to evaluate the built world without tearing holes into it necessarily. Various types of sensors, and then lastly we have quadruped robots there. So little dog, spot, and other variants going around capturing data for us. We're trying to harvest as much data, digest as much as we can, with the goal of building a digital twin or a 3D model of the asset that we're talking about, or assets. So we're feeding all this information in, we're making a baseline 3D model. I'll show you examples here in just a minute. And then what do we do with that? That's like the so what. Okay, we captured all this data, but what's really important is what the condition of the structure is or what we should do about it. We can do various overlays to that. So we could use AI, for example, machine learning on all the imagery that we took, and we can detect defects. And then we can project those defects onto that 3D model. We could take the non-destructive testing results, like thermography, thermal imaging, for example, and we can project that onto the 3D model. We could look at as-built construction. So if something wasn't built plumb or correct, we can overlay that as well in the model to see how out of plumb it is or what needs to be corrected. All this is packaged up into an asset management platform. This helps the owners of these assets really see what the true conditions are. So again, we're finding all these defects and anomalies and issues. We're mapping them onto the 3D model so they can see. If we repeat this exercise over time, we can start doing projections about whether things are getting worse or not. And so you have like predictive analytics and insights about what a structure is doing. Pretty much every owner out there, when you confront them and say this needs to be repaired, they say, well, how long is this going to last? Well, we don't know. We have to be able to do multiple studies and evaluations and look at trends for this. But this is generally the path that we take. And so I'm going to highlight portions of this as we go. So let's take aerial survey again. This is going to be primarily drones. The platform that we use is Skydio. This is the X10, which is their newest model here. I think you had a presenter not too long ago from Skydio, right? Yeah, okay. This is a fantastic platform. It's really great for two things. One, we just learned by happenstance. One, we went into wanting to have. The happenstance was this is a US-made drone. We didn't think about that when we went on the Skydio platform, but boy, is that convenient now because we have lots of federal and government projects where we're not allowed to use foreign-made drones. And there's a ban in place as of December 23rd. You can't import new foreign-made drones. You can still import the ones that existed, the new ones. So boy, I guess we were smart on this one. We have Skydio as our primary platform. Second reason we went into this in the first place was that it's an autonomous drone. That is, it can fly on its own and it can capture reality for you. So you pop the drone up in the air, you draw a geofence around the asset you want to scan. Drone figures out the flight path, it figures out the overlapping photos, it figures out the battery swaps. When it runs out of battery, it comes down, lands on the target, you swap the battery, goes back up and keeps scanning. The sole intent of this is to capture photographs so you can do a process called photogrammetry where you stitch it together and build the 3D model. So it's really good at this. Sometimes it gets hung up on like complicated geometry, but generally you can put it up in the air, you just rest free, hold the controller and watch it do its thing. It will fly around and help you capture all the data that you need. You get 45 minutes of battery life. You do have multiple cameras on this. You can do infrared and visible at the same time, which is pretty cool. You can do a visible model and then you can overlay an infrared model on it. So great platform to work with. We have about 15 to 20 of these drones that we use, and we have them deployed throughout different offices around the country and even international as well. So it's been a good platform for us. So let me show you a practical example here. So this is in the industrial space, we'll call it. This is at a power plant. This is a cooling tower. This is what ejects heat coming out of power generation. If you don't have this, you can't generate power. So it's kind of a critical asset to do. It's made out of reinforced concrete. Over time, because of the exposure in the environment here, it tends to deteriorate very quickly. And so what we're trying to do is assess where the pinch points are, where the problems are that we focus on, rather than painstakingly getting on some type of lift and taking field notes for days. Right. So we're going to deploy a drone. I don't know if you can see it in this photo or not, but it is right there. It gives you a sense of the size of the scale of these things. All right, so I'm going to show you sort of the behind the scenes view of this. You get the open kimono magic here. So to do this, we're physically on the cooling tower. If we're scanning, say, the top part of it here, that's the crew there. That's the box the drone comes in. The drone's sitting on the box, which is the target that it will land on. And then the controller. On the controller, you can watch it as it's doing the image capture to make sure you have all the overlapping photos that you want. You deploy the drone. You take thousands of photos for this particular asset here. The drone's on the left. You can see it there. On the right is what the drone sees. So this is it's computer vision algorithm, if you'd like, but it's mainly for collision avoidance. So it is making sure it doesn't run into anything, but it's also mapping the space so it knows how to autonomously capture it. So it's kind of doing a twofold thing of, do I understand the space correctly that I'm imaging, but also I don't want to run into anything. So you can just pretend the drone has eyes in that sense. Skydio drone actually has 6 cameras on it. It's doing machine learning on the fly for navigation. And so it has GPS, it uses GPS as a backup, say, but it's actually flying on visual navigation, which is actually pretty handy in places when you're GPS denied. All right, so we're taking thousands of photos, and then we're taking these photos using computer vision. Essentially, we're running them through our own algorithms to detect damage and defects. And so we have thousands of photos, we find the defects, we then map those defects onto the 3D model. And so in the end, this is the portal that I was telling you about before. I'll show you a little video here, but basically you have a digital twin of that cooling tower. All of the red you see are cracks that have been marked that were detected from the machine learning. And so as a bonus, you get cracks in the roadway because AI doesn't know the difference between the cooling tower and the road. And so you get a full mapping of all concrete cracks in this. You can then zoom in, zoom out, interrogate it. You can pull up the photos that correspond to particular defects. The beauty of it all being machine learning based is you also have a quantification of how many cracks you have, the lengths, as well as concrete spalling, areas of concrete that are deteriorated that you have to repair. And you get that all in a nice little package, and you can look at this within the office or desk or remote place wherever you are. You don't have to be out in the field all day, every day, trying to get all of this documented. So this is the beauty of having it be autonomous. It's not just cooling towers. We've done stadiums as well. So this happens to be a sports stadium. This was all done by drone. So you're talking about thousands of images, stitching them together, capturing it, building the 3D model, which is the digital twin. And then from there, you can do detection of defects, cracking, spalling, and so forth for concrete. We've looked at tensile fabric structures. So this is a stretched fabric here. This is a natatorium, which is actually a pool structure. So it's a cover over a pool that's all stretched fabric. We can fly both inside and outside and do evaluations on that type of material. I've also looked at institutional assets. So here, this is at a university here. This is a classic brick masonry building. Digital twin of it, you can spin it around, interrogate it. You can look at defects in masonry. Which is cracking and spalling. I'll go through those in just a minute. Also adaptive reuse. So this is an old church. It's being used for different purposes. So you build a 3D model of it. You now have that. You can interrogate it for damage defects, but you also have something that is nice, true to scale. So if you wanted to modify this in any way, you now have all that information. In my profession, a lot of times we do not have drawings for things. Once something is built, for some reason, they just throw them in the trash and you never have them again. They keep the mechanical, electrical, plumbing ones forever because they have to replace systems inside. But when it comes to building the structure, they seem to toss it when they're done. So a lot of times we have to go through a process. We would call building as-builts or building the documents, drawings that don't exist, making new drawings, if you will. It also goes to transportation assets. So if we wanted to do a bridge inspection, we could fly a drone, we could take lots of photos, we could stitch those together by photogrammetry, and then in our own comfort and leisure, we could go back to the office and actually do an up-close inspection of this. You can look really close, very nice high resolution here. You're not dodging cars, you're not having to close lanes. Oh, by the way, because you have thermography at the same time, you can turn that on and you can look at this in the infrared spectrum as opposed to the visible spectrum. As it turns out, you actually see more concrete defects in the infrared spectrum. And that's because of the heat signature is a little bit different when the concrete's going to pop off. than when it's intact. So it's a fantastic tool for that. You can see the infrared spectrum down in the bottom right. Bottom left is just the path that we took.
Is it residual rubber from the tire tracks, or is it like indentations, or?
That's a poor asphalt job there.
Okay.
Oh, are you talking about the infrared?
Yeah.
Okay, so the infrared, the bright yellow you see is the beams underneath. They have a different heat signature than the rest of the deck because of different thickness. So the deck's 8 inches thick all the way across. The beams are 6 feet deep. Yeah, so you're picking up the beam lines. It's really cool. You can pick up metal studs in buildings. You can pick up all kinds of things. You can pick up your footprints with thermography. It's kind of fun to be a detective. Somebody at some point should ask, where are the cars? So this is a fun little story here. You're not supposed to fly drones over moving vehicles. This is typical DOT policy. You're not supposed to fly over crowds as well. We actually flew this in a less occupied bridge, off hours essentially. But when cars were coming, we moved the drone out of the way. And then we brought the drone back and kept going. So this was not a one shot, but this does take about 10 minutes really to do all this. It's not a very long process. You just have to get out of the way of the cars when they come. We've also looked at quite a bit of parking lots as well. So this is drone fly to parking lot, stitch all the photographs together, run it through machine learning, and all that red you see are cracks in the image. You can probably relate to this if you look right out here in your service lots. They have cracks all over the place, like many do. We can quantify them right away, and then we can come up with a repair program for this. So this really helps us focus on where the problems are. If you walk this on foot, you'd have no idea. You would just keep documenting, and then you would go back to the office and try to make sense of all the field notes. Now you have that all in a living model. And then as you make repairs to this, you can update it and have a record of it. So there's a lot of opportunities with computer vision using drones. Just to touch briefly on machine learning. So there are different types of materials of construction. And so what we've trained it up, these are different AI models basically, but we've trained it up on what concrete does when it misbehaves, when it deteriorates. And so if concrete does that, it cracks and falls, the reinforcement's exposed, they have efflorescence, which is a white staining that occurs, and you have corrosion staining from all the rebar that's exposed. We've trained it all up on concrete. So when it sees concrete, it automatically marks those defects and then maps them to the 3D model. Tensile fabrics we are working on, there's a whole different behavior there. So with a tensile fabric, you have tears, punctures, worn top coats, hard creases, seam delamination, and it's a lot harder to do it with computer vision and fabrics than it is with concrete, I'll tell you that. So still in development, we are working on it. Masonry, which is like your typical stone masonry or brick masonry, you're gonna have cracking, spalling, efflorescence, and corrosion staining. We've got that one down pretty well. All trained on photographs of actual distress. So we have a whole library of distress to train on. Natural stone is really tricky because natural stone has all kinds of defects in it on purpose. That's why people love it. It looks so beautiful, right? Well, it has occlusions and defects in it. So really hard to train on what a defect is, something like that. And lastly, steel, we'll get to in the future. Steel just kind of rusts. There's not a whole bunch to it other than rusting. So we'll get there at some point. But just to give you a flavor of the different materials and what we're looking for. All right, so let's talk about data capture from the laser scanning perspective. So we'll do LiDAR. We have a few pieces of equipment that we use for LiDAR, primarily on Leica's platform, Leica Geosystems. This is the RTC 360. It's sort of the high-end laser scanner, high precision. You can get plus or minus 2 millimeters on this. So this is really, really good for building reality. Advantage of LiDAR and laser scanning is it is dimensionally very accurate. If I fly a drone and I do photogrammetry, it doesn't know the scale. That is, I can take a picture up close and I can take a picture far away, and you can't tell the difference really, other than zooming, right? You can marry the two up. You can marry up LiDAR and photogrammetry, and you get a true to scale model. We do that a lot. So LiDAR is your excellent measuring tool. Photogrammetry and is your excellent visual tool to see things. So this is a high-end laser scanner. The other end of this is the BLK2Go, which is a handheld mobile laser scanner. So if I wanted to scan this space right now, I could simply just walk around the room really quick, and I have a point cloud of this very fast. You can imagine you could mount this to other robotic platforms as well. There's a variant of this called the BLK Arc, which you can put on Spot, or you can put it on rovers, all kinds of things to do. Basically integrated SLAM. And so it's building the point cloud. It knows where it is in space as it's going. It can take pictures and tie those to the point cloud. Pretty cool technology. So in the old days, I make myself sound old here, but on the left, we would go like walk a parking garage to find defects and all that, and we'd take a picture. Well, in the modern era, we can do this with laser scanning. Now we have a digital twin, we have a 3D model out of a garage. Before we just had a photograph, and invariably we forgot to take a photograph of something, and then we're stuck, you know. Now we have a full model. We can do a walkthrough, we can interrogate it, it's dimensionally accurate, we can do whatever we want with it. That model could be created by a quadruped, it could be created by a rover. There are many different platforms that could go through this type of structure. So that's kind of exciting. But let's take that one step further. So here's a colorized point cloud that was created. Now there's a particular advantage of having this, and I'll show you in just a second here. You can use AI to classify different components within that garage. So the AI algorithms are trained on what pipes look like, what columns are, what beams are, any parts of building construction trained, windows, doors, you name it. So now I can do a walkthrough here, and it's pretty good. It's not 100% perfect, but it can identify all the different features in the garage. So if I just wanted to know the pipe layouts, I can isolate those. Or if I want to know the framing, I can isolate that. So you can pull all this apart. That's all detected by machine learning. Pretty cool. All through a process called classification. There's another interesting one. So we got involved looking at a landslide. And there happens to be a tunnel where the landslide occurred. So the tunnel was mainly to protect from falling rocks or debris and things like that. But as it happened, the landslide actually occurred out the tunnel and actually punched through the tunnel. So here we are investigating this, trying to make sense of it. The model that you see there is LiDAR. So that is a point cloud that is colored to look like an image, but it's not an image. It's just millions of points. But it looks amazingly good. And the beauty of that is that it's dimensionally accurate. So if I need to get measurements about where the tunnel was damaged and how and why the landslide occurred, you can think of many other scenarios here, I can get that. This was taken off of a drone as well. So that's LiDAR from a drone, which you give up a little bit of accuracy on that just because of the mobility of it. But that looks amazingly good for what we would do. So you can take the point cloud, you can cut cross sections through it, you can take all kinds of measurements, quantities. If you want to know how much land is there on the slide, the dirt that's on the tunnel, you can definitely calculate that. There's a lot of good opportunities when using LiDAR. All right, and then quadrupeds. Let me just touch on these, and then we'll sort of tie all this together here. So quadrupeds, we've invested in Unitree's Go 2. This is a good entry point for us just from a cost perspective. We priced out Spot, and if it has everything we wanted, it's like $150,000 for Spot. I think he looks really cool. He looks great on commercials and all that, but we can price this out at $20,000 versus $150,000.
7 of them.
Yeah, you buy 7 of them, you got to start here at least, learn the craft, right? So this is Max. This is our mobile autonomous Explorer with the X in Explorer there. He's the Unitree Go to EDU edition. So he's got the extra compute on him. Does have LiDAR and the stereo vision camera there. So it actually has 2 LiDAR scanners because one's in the snout and one's up on top. The one in the snout's done for navigation. The one up top is what we're using to capture the built world and do our LiDAR processing. Jetson Orin processor. It's a little taxed. It'd be nice to get the Thor processor in there. We're hoping that maybe they'll make that move here pretty soon. And you look at it, you're like, 100 trillion operations per second. Wow, that sounds really fast. And then you start processing all this data in there and you realize, oh boy, this thing's dragging. Weighs about 30 pounds, which is actually a good spot to be in terms of this, because we have to go deploy this. It can't weigh 150 pounds for us. We would never be able to get it to a job site in order to do the evaluations we need to do, at least not easily. There are 2 pieces to what we use for the quadrupeds for. One is for mapping and navigation. The second is for the AI vision model. So the intent here is that Max walks the space. As he's walking, he's capturing it with LiDAR. He's also using the cameras in order to detect defects. And then he will tag those defects to the point cloud. And so now we have an as-built of the space, which is dimensionally accurate, but it's also tagged all the defects that it sees as it goes through. Here's Max in action here. Sped up the video a little bit so he doesn't walk that funny, but it gives you an idea. On the right there is the point cloud that it is building in real time as he walks. So dimension 3D mapping is an application, defect detection. This is very repeatable. First time he walks the space, explores it, now it's all mapped out. Now I can draw a path for him, or I can tell him to go do this again 1 year later, right? And then we can make comparisons about what's occurred. Max is really excited. We'll let him finish up there. Down at the bottom right, this is just us playing around, but we have computer vision going on where Max is identifying a person. So he's using object detection, and he's identified a person with a certain amount of confidence. We are training Max on identifying defects, all different types, and then we'll map it just for fun to show you he found a person. He found his master, his trainer, as he went. This is the garage that they were walking through. This is the point cloud being processed here. So you can kind of get a sense, you can see the cars in there, the columns, so forth. We'll clean it up even more to make a full model out of it, but just to sort of give you the sense of it as we go. We took Max to one of our offices, and Max decided he wanted to map out the space, as any good quadruped would want to do. So it took him 6 minutes to map our office. You can kind of see the vector that he's walking here. And he's building the space as he goes. I say he, but we have Maxine coming soon. Maxine's going to be on wheels with the feet, be a roller type. But very fast for building the space out. And of course, then you can tie that with object detection. This particular demo we were doing here, Max was finding potted plants. So when he found a potted plant, he would tag it and mark it to the point cloud. So we start with the Go 2. We'll probably make the step to go to the more enterprise version of this, which is a bigger, heavier, huskier one, but better battery life and ruggedness to it. But you have to ask the question, how long is it going to be before we go to 2 legs here? Well, if we're at 4 legs now, so this is probably going to happen fairly soon. We don't have anything purchased at the moment, but I was talking with Damon about this earlier. It's really fun watching kung fu videos online or watching them dance. But there are some very practical applications for us where it could walk through structures, particularly if you have like a hazardous structure, a tunnel, something that you don't want to go in, be the first one into. It can definitely do it for you. It doesn't get tired, complain, and all that, other than it runs out of battery. So you just swap the battery, you can keep going. Again, focusing on autonomous data collection here. So we don't want to be the ones, humans, out there at the site doing all the collecting the data. Let other platforms do that. All right, so now the important point, robotics fellow wanted. Why I'm here is we are looking for a robotics fellow to build autonomy that captures reality and powers computer vision for the built world. So I have 4 projects in mind, and I want to talk through them and then get your thoughts, and we can have a more robust discussion around all that. But things that we're looking for right now in this space. One is an extensible drone. And by that, I mean, we have Skydio, we like the Skydio platform, but it's very much a closed system. So for example, if we want to deploy computer vision on the drone, we can't do that. Skydio drone is flying, taking pictures for us. We have to come back, build our 3D model, and then analyze all the photos on it. It'd be really nice to be able to do object detection or different types of ML on the drone and just be able to extend it in different ways. So right now, it is what it is. It's a box, you fly it. We want to be able to do more development. We do have an NDA with Skydio. We do have advances on their releases. We have talked to them about this. Understandably, they want to keep some things guarded. But so we're looking at an alternate platform as well. Not that we're getting rid of Skydio by any means, but do we have an alternate platform that we could extend? So that's one idea. Rovers. And so we have quadruped, but it would be nice to have a rover as well. And there are some advantages of each, but we need a lightweight rover, something that is easy to deploy at a site. And by lightweight, I mean under 30 pounds, something you can just have in a Pelican case, bring it out, deploy it, be able to do reality capture, typically inside. So like this space, for example, or this whole floor. Be able to go autonomously, use LiDAR, use computer vision with cameras, detect defects, and package that all up for us with a SLAM algorithm. Third one is to go underwater. We haven't done this yet. We have a need for it to do underwater inspections. So can we do an autonomous submersible? So is there one out there right now that that is open that we can extend, off the shelf? I I hesitate to say we're going to build our own, but there's probably something out there that we could modify. Lastly is to do more advancement on quadrupeds. So right now our quadruped walks around, we're training them up out of the box, the go-to or spot or any of those, they do nothing. They don't have slam, they don't have any of the things that we need, right? So we've had to do all the development on our own. It'd be nice to have them on the wheel platform. Maxine's coming soon, but there's more development we need to do on quadrupeds. So those are kind of the four general things. Those feed into that same stack I showed you, the digital workflow. So the data acquisition piece, now we're just adding new bubbles into there to collect more data in order to build our twins, do our overlays, and do the asset management. So let me walk through those just a little bit more detail. So the first one, in number order here, is to build a lightweight autonomous rover platform for caption lidar and photogrammetry of interiors. That's not lightweight, by the way. That's what AI thinks lightweight is. So that's ClearPass. That's us, right? And it's still too bulky for us. So it needs to be lighter than that. Still want it to be ruggedized, still want it to be able to explore the space without breaking, go up and down ramps, things like that. But needs to be something that's in a case. You can just take it out, deploy it. Preferably you have a tablet interface and you just deploy it and it goes. And it autonomously explores and you can look at the tablet and see that it's collecting data. You're probably not going to build the whole point cloud on the fly. That's okay. We can do that later, but just make sure we're collecting data. Second one, provide a development support for an engineer working on autonomous quadruped platform for capturing lidar and photogrammetry of building interiors. You can use the quadrupeds outside, but we found the drone is like the perfect platform for outside. What you really need is the interior scanning a lot of times. And it doesn't have to be a building. It could be a stadium. It could be of many different types of structures. They all have some sort of interior to them that it's kind of hard to fly a drone in. We can, but there are other platforms that are more efficient about it. So we'd like to do continued development on the quadruped. Third one is to develop an extensible US-made drone platform to run AI vision models and build a photogrammetry model during flight. You think we can do this one? So now we want to do computer vision on the fly and build the model on the fly. Maybe this is crazy. Maybe we need to wait for next year's model, But we really like to do some of that processing on the drone right now. And as I said before, Skydio's platform is a little bit closed to be able to do that. So right now we have to just take all the data and do our processing later. There are many, many instances where when we're flying the drone to site, we'd really like to know then where the problem issues are, so we can do more focused investigation there. Instead of doing all the drone flights, going back, building the 3D model a week later, figuring out what we want to look at, and then going to the site again, right? So there's a real need to be able to do this on the fly. Lastly, maybe the coolest one, I don't know, is to build the autonomous submersible platform that can image and evaluate distress in underwater structures. So this is a particular one that we need to be able to look underwater. It has some challenges. Most water is murky, so vision is difficult. With this, sonar would be great for using it, but there are other sensors out there as well. But we need to be able to look at structures and look at their integrity underwater. Traditionally, this is done by divers. So you have to deploy humans, they dive, they get tired and cranky just like any other exercise. And it's really hard for humans to do a lot of data capture when they're diving as well. So we want something that's autonomous that can help us with that. And then we can package that all up into our model. So with that, those are the 4 different project ideas that I'm bringing to you. Our interest here is to start a robotics fellowship whereby we have a fellow come work for the summer with us on one of these 4 projects. And then continue on, I believe it's in your capstone course in the fall with faculty advisement, I believe, to carry that further into fruition, if you will. So I'm casting I guess a wide net here. We have 4 different ideas. Would like to have resumes from you if you are interested in one of these particular ideas. And then we can do a follow-up with interviews and discussion and so forth to see which one really makes the most sense and where we want to go with this. We're willing to support not only you being the fellow and paying you to be the fellow, but also the equipment that you would need and anything that goes with it, we would be willing to support. And so with that, we want to go to discussion.
Let's before we go to discussions, let's give a quick round of applause. That was great. Yeah.